Hi everyone. So hopefully that went well. All of the answers are here, so whichever one you picked, you should be able to check yourself. So I'm just going to talk a little bit about some things I notice on these graphs, but the big thing I want in this video is to talk about how this is helpful, how we get an idea of what the solution to the differential equation is, because that's always our goal, is to solve a differential equation, find the function that makes the statement true. Okay, so things that I noticed just in terms of sketching, we talked about the fact that the first three are only determined by your x value. The slope is only determined by your x value. So at any given x value, all the slopes should be the same. So you'll see these matching slopes along vertical lines. Other things that I noticed with this one is that no matter what x I plug in, x squared is never negative, so I'm always going to get 1 over 1 plus some non-negative number. So the smallest number that I can get from x is 0, which means the biggest this thing can be is 1 over 1 plus 0, so 1. So when x equals 0, I'm getting my biggest slope of positive 1, and then if x is anything other than 0, I'm going to have, for example, when x is 1, 1 over 1 plus 1 is 1/2. When x is 2, 1 over 1 plus 4 is 1/5. So the slopes are going to keep getting smaller the further to the left I go. And you'll see the same thing happening on the right, because that square is going to eliminate any negative signs. So when x is negative 1, I don't know why these didn't get negative. Something's showing up a little strangely. I'm just spotting. We're going to get the same thing as when x is positive 1. So that's kind of what I'm seeing. On this second graph, just to mention a couple things there, I have a similar thing happening where the bigger x is, the smaller my slope is. So as I'm heading to the right, I see slopes getting flatter and flatter. Notice that when x is negative 1, my slope is undefined. So that can be, again, a few different things. It might mean you have a vertical tangent. It might mean you have a vertical asymptote, which is what I suspect we're seeing here. It might mean there's a sharp corner in your graph. So all those things that can make derivatives undefined can make this happen in your slope field. The other thing that's interesting in comparison is that now we don't have the square. So when x is positive, we will get positive slopes, but when x is, I should say that more carefully. When x is bigger than negative 1, we'll get positive slopes. And when x is smaller than negative 1, we'll actually get negative slopes. So instead of just seeing all positive like the last one, now we're getting negative slopes. And then that last one doesn't have the fraction at all, so we don't have anywhere where our slope is undefined. But notice, if x is 0 or 1, our slope should be 0. So we're seeing these nice flat slopes along the y-axis and these nice flat slopes along x equals 1. So we're seeing a couple of different spots. Okay, so let's talk about solution curves. And I think this is especially interesting here because we can actually solve these things. So when I'm looking at this first one, you can basically pick a point, and right now we'll just pick at random, but in your homework you'll be given specific, in your mixed practice, you'll be given specific points to hit. So let's say I want to hit the point -1, 0. What you do from there is just follow the slopes you're given. So I have slopes that look like this. As I head to the right, it looks like they're getting a little steeper. And then as I head further to the right, they start to flatten out again. So just kind of follow the tick marks that you have nearby to help you figure out how steep your curve should be. So it's kind of like connect the dots. It's like you have current, right? So imagine this is like water current and you have to follow it. How would your point move along if this was the current you were following? So this is a potential solution curve. And if I pick a different starting point, maybe I pick 0, -2, I'm going to have a different curve. But notice it looks pretty similar. In fact, this is looking like what we're used to expecting. It looks like the difference between my solution curves is just a plus c. And because this is such a nice simple dy dx equals something that only involves x, there's nothing implicit or weird going on, you could actually solve this, and we'll work on solving them algebraically in the next section, but you could actually solve this just by integrating. If my derivative is 1 over 1 plus x squared, I can integrate that and say, okay, well, whose derivative is 1 over 1 plus x squared? It's arctan, inverse tangent. And I don't know if you remember this, but this is in fact what inverse tangent curves look like. There's horizontal asymptotes in there that we might not quite be able to tell because we maybe didn't go far enough, but we do see slopes getting pretty horizontal. So in fact, our solution curve would involve multiple of these. It just happens that I drew ones that look like they'd work together, but multiple possibilities of shifting this little chunk up or down, right? So it's a single chunk, move it up or down, all of those would be solution curves. For the second one, if I were to draw a solution curve, this looks like my slopes are getting really steep, so I'm just going to start down here. So I'm guessing this is vertical asymptote. That's where I'm getting that idea of it looks like there's probably an asymptote at -1. As I move to the right, I'm getting a shape that looks sort of like that. If I solve this thing, I get that my function should be natural log of absolute value of x plus 1 plus c. So again, if I picked a different point, say I picked 0, 1, I could work my way back. It would look more like this. So these shapes that I'm getting are looking like natural logs. What's interesting here is the absolute value on the natural log. That wouldn't have been something that you worked on for like pre-calc graphing, but what it does is it just gives you two pieces that are mirror images. So to get a single solution curve, we'd actually have to have a couple of these paired up. So the one on the left and the one on the right. But that's what we're getting. So we can draw some solution curves. Even if we didn't know how to solve this, we could draw some solution curves. For the last one, say I pick the origin again, it looks like I need to go down a little bit as I head to my right, and then we know they're flat at 1, and then it heads up and just gets steeper and steeper and steeper. On the left, it looks like I need to go up a little and then just get steeper and steeper and steeper again. So something roughly like that. That looks pretty cubic, and that's a good sign because if I multiply this out, I'm looking at quadratic. The derivative of my function is quadratic. So my function should be an x cubed over 3 minus x squared over 2 plus c. And we can see that that matches up again here. So if I picked a different point, say I picked the point 2, -2, I would get something doing sort of a similar thing, but shifted down. So we're going to see, again, this isn't totally perfect when I'm just hand sketching these, but we should see those solution curves that are just shifted up and down. Okay, so if we get into the ones that are functions of only y, those can get kind of interesting. We don't yet know how to solve those algebraically, so we'll work on that in the very next section. But we can still do our drawing. So again, there's kind of a gap there. That's where the derivative is undefined. So it could be vertical asymptote, which doesn't look like what I'm having here. It could be sharp corners, it could be vertical tangent lines. The way these slopes coming up to it are getting really steep, I'd suspect that these are probably vertical tangent lines in here. So we can kind of draw through. You'll get better at spotting that as you get used to drawing solution curves. Okay, so let's say I wanted a solution curve that passes through 1, 1. So you'd start at 1, 1 and you just kind of follow your slopes along. And if you're kind of seeing there, maybe you can see why I thought it was vertical tangent, because if I follow that, it looks like I just kind of need to arc around. So there's one possible curve. If I was going to draw another possible curve, let's say I wanted it to go through -2, 0, I would follow and then start curving the other way as I go up. They're positive slopes, but they're getting less steep. So interestingly here, it does not look like my solution curves are related by vertical shift. It looks like they're related by horizontal shift. It looks like if I shift it to the left or the right, I'll get another solution curve. So that's kind of a neat thing we haven't seen before. We'll be able to solve this shortly. I would just say right now that looks like a sideways parabola. So as we learn separation of variables in 4.3, we can check and see if that's an accurate estimate. For dy dx equals y plus 2, one thing I notice is this. Whenever y is -2, my slope's 0, so I'm getting that flat spot. That if you pick a point, if you wanted to draw a solution curve that goes through 1, -2, this is called an equilibrium solution, where unlike the rest of the solution curves you draw, you just get this really boring constant curve. It's like your current just sticks you along that horizontal line. Your y value doesn't get to change at all. I see the same thing happening on the next graph. It looks like, what would it be? At y equals 1, I'm going to have a equilibrium solution. So if you're given the point -2, 1, for example, anything with a y coordinate of 1, you get stuck on that horizontal line. That's called an equilibrium solution. So you'll get asked about those sometimes in your homework. Otherwise, for points that aren't on those horizontal lines, so like if I got 0, -1 instead, as I head over, my graph just starts getting steeper. Something along the lines of that. And if I were to start below this curve, so let's say you start at -2.5, you're going to get something kind of similar, but so I think I'm seeing a horizontal asymptote. It's going to go down. If you pick a point above the curve that's different than that, I think we're seeing again here that when our slope depends only on our y, our solution curves are horizontal shifts of each other, not vertical. At any point here, if you think you've got the hang of it, just skip ahead, pause and skip ahead and try and draw a little bit of your own, and then you can check back. You probably don't need to watch me draw on every single one of these to get the idea. Here, if I were to, let's say I want this one, I see again it looks kind of like horizontal asymptote. And again, if I start above the curve, so let's say I want to go through this point, get something more like this. And I actually could totally be wrong about this, but what I suspect is maybe these are those like the 1/x type graphs where you're getting two pieces that go together. It's not that these are completely separate solutions, it's that it takes two pieces. So possibly we have vertical and horizontal asymptotes here. So again, you can verify whether or not my guess is right tomorrow, but that's kind of the idea with this one. Okay, so last few, I see some interesting things here. I'm going to try and speed up a little bit. I don't think we have to draw every single one, but one thing that I see that's interesting on this one is if you start up above, it just kind of looks like you get this funny little shape. Whereas if you start, I don't know, let's say we start right here even, it's looking like you get really steep and then you head out. So that's kind of a crazy weird thing that's going on. So maybe depending on where you start, you get really different kinds of solution curves. And then back down here again, it looks like we're just getting kind of like a loop-de-loop instead of that weird little, I don't know what's happening in the middle. So those are kind of neat. Similar on this one, if I start up here somewhere, I look almost like I'm just getting kind of a parabola shape. So maybe this is something weird and rational again. Whereas if I start more like this, I get this little dip. And if I start even lower, I think it's just an exaggeration of that dip. So that's another one that's kind of interesting. I do think I'm seeing horizontal asymptote on the x-axis if you start down below. So probably an equilibrium solution happening right there. That's kind of hard to see because the axis would hide those tick marks. Here, I think I'm seeing some slant asymptote behavior. So like this is happening. And then we'd head back up maybe. So that's kind of neat. What happens if we go above instead of below? Head up. And here, that's going to run off the graph. Let's start a little closer. Kind of similar idea, but jumping up above instead of below. So we're getting kind of weird shapes, harder to predict. Again, a lot of these are separable, so we'll be able to solve them in 4.3, but not all of them. That one I just did is not looking promising for being able to separate. So that's somewhere where it's really nice to be able to draw these curves, because even if it's not perfect, you have an idea of what your function y looks like, when it's not very easy to just go ahead and solve these. This one's really cool. It just looks like we have these straight line segments shooting out from some origin point. So that's kind of crazy. I think what we're actually seeing there is different absolute values. And I'm a cheater because I've done a lot of these, so I know. But I think that's what we're really seeing, is that these would be pairs of absolute value functions. Not even pairs. Like this would be, the bottom would be 1, the top would be 1. So they can be flipped up or down. They can get skinnier or wider. So here, it's not horizontal shift or vertical shift. It looks like it's vertical stretch compression. Like they all hit this corner point, but they get taller or skinnier. In the next one, our solutions appear to be circles, so that one's pretty neat. And then in that last one, I think I'm seeing like a hyperbola shape. So let's see. It looks like there's some slant asymptote stuff happening in here. So if we start above that, we'll get curves like this. And I'm guessing, but I don't know, that those come in pairs like that. If you start out at the sides, they go this way. And again, I'm guessing, because that's what a hyperbola does, that they're coming in pairs, but we'd have to solve to actually figure that out. Okay, so that's probably way too many examples, but hopefully that was kind of interesting to look at. The next problem asks you to do a little bit of matching. So I'm not actually asking you to draw them by hand, but just to check that out and try and match the differential equation with the slope fields that you see. And then it doesn't say this, but I would recommend going ahead and trying to draw a couple solution curves, because these are kind of weird looking slope fields. They're a little messy. So I think that's about it. Thanks for watching.